Laura Totten with the U.S. Army Corps of Engineers, Kansas City District. And this is a recorded webinar for the Tuttle Creek Reservoir Water Injection Dredging Demonstration, start of the spring demonstration period.
And hi, this is Michael Mansfield, and I'm the technical lead for the project.
The authorization for the demonstration is from the Flood Control Act of 1938, which is the authorization for the reservoir itself, for the construction of it. Funding for this project, total cost is $9.1 million. The federal funding came through a Consolidated Appropriations Act of federal fiscal year 2022, $1.3 million. And then additional funding came from fiscal year 2023 Consolidated Appropriations Act in the amount of $2.8 million through the operations and maintenance business line water supply. And then approximately $3 million was reprogrammed from another study through operations and maintenance for another Tuttle Creek operations project. The state of Kansas, Kansas Water Office also allocated and contributed an additional $2 million to the effort. And again, I'm the project manager for the Corps of Engineers. And then Josh Olson with the Kansas Water Office is the project manager for our partner. The technical lead is Michael Mansfield from the River Engineering Branch in the Kansas City Corps. The demonstration schedule, we had our first demonstration period in fall of 2025. That was from September 17th through September 27th. The dredging operation was for 10 total days of dredging, and then the demobilization of anything that needed to be moved off for the winter. It included 200 hours of active dredging and assumed 20 hours of dredging per day. And that demonstration period is complete. And we are preparing now to start the second demonstration period, which is the spring period. And that will be from March 17th through March 27th. With, again, an additional dredging operation of 10 total days and then some minor demobilization after the spring period, in between the spring and summer period, with an additional 200 hours of active dredging, assuming 20 hours of dredging per day. And then we tentatively have scheduled the summer demonstration period for 2026 in June through July. The dredging operation will be an additional 10 total days. And then following that summer period, which will be the end of the 3 periods that are planned, we will demobilize the water injection dredging unit from Tuttle Creek Reservoir, but the operation will include another 200 hours of active dredging, assuming 20 hours of dredging per day. So the total dredging hours that we're doing is approximately 600 hours of dredging over about a 30-day period. And then we'll be doing post water injection dredging demonstration reporting in completing that by end of calendar year 2027. And the results of that demonstration will be released following completion of these 3 dredging periods and a thorough data analysis that has gone through appropriate peer review and quality control review as well. Tuttle Creek Reservoir, this is a little bit of the why. Why are we doing this? The multi-purpose pool sedimentation. The multi-purpose pool is approximately 49% full of sediment. About 3,794 acres approximately accumulates per year, or 6.1 million cubic yards per year of sedimentation in that multi-purpose pool. This is on par with our original projections when we originally constructed the reservoir for the sedimentation that would be entering into the reservoir. But a future without action means that there's a near total loss of the multi-purpose pool in the future, 50 to 100 years, with deposition thickness being 20 to 50 feet in the submerged channel and 50 to 20 feet in the submerged floodplain, consisting primarily of highly erodible and fluidizable clays and silts. And down this diagram below, down here, you can see some projections of how the multi-purpose pool would shrink over time with just this little bit of water left after 2074. And then you can also see a second way of displaying this, loss of the multi-purpose pool over the years originally in 1957 when the reservoir was constructed. You can see the size of the multi-purpose pool at that time, and then just compare that over time to the different time frames where we either had a survey or we have projections. And then this red is, what would be left of this total reservoir area multi-purpose pool, at least projected to be in 2024.
So to give a little bit of background on water injection dredging, or WID as it's known, it's an innovative type of dredging where the dredge injects large volumes of water at low pressure into the sediment bed in order to fluidize it. WID vessels, they're pretty simple compared to traditional dredges. They have two large pumps on the barge that pump the water from the surface down to the bed. Dredge is positioned over an area to be dredged and then moves in one direction in order to fluidize the sediment. They don't typically require a lot of support equipment. They're easy to mobilize. They have low energy input compared to traditional dredges. And so WID has never been performed on a reservoir before. So our WID vessel is unique compared to other vessels. A lot of WID operations occur in ports and harbors, primarily overseas. And so ours was constructed in the state of Kansas, and it was designed specifically for Tuttle Creek Lake. So water injection dredging's goal is to create a density current. So by pumping large volumes of water from the surface to the bed, it creates this density current, which is essentially a fluid mud layer that is denser than the surrounding water. And that density difference allows the density current to transport downslope. And typically this would be towards the gates. Once it reaches the gates, then it would re-enter the natural environment of the Big Blue River. As part of this project, we are trying to study the travel distance of this density current and other operational parameters so we can fine tune it and determine what the optimal dredging pattern could be. So as we kind of discussed in the past, the goal of this demonstration project, it's known as a demonstration project, is to answer questions, not to remove a certain amount of sediment. So again, because WID has never been performed on a reservoir, we need to answer these questions. Could it be an effective sediment management methodology in the future? So here's some of the primary questions that we are trying to answer as part of this project. Really, how much sediment can WID remove? How much does it cost? And then what are the downstream impacts? Are there any downstream effects, both for water quality, ecologically, geomorphology? And if we can answer these questions, then we consider this a fully successful demonstration project. In addition to the primary questions, there are also some secondary questions that we are working with several collaborators to answer. These secondary questions primarily relate to the sediment transport of the density current, some sediment consolidation, as well as some chemistry and ecological variables both in the lake and then downstream as well. Some of our collaborators include federal entities in the Engineering Research and Development Center, the USGS. We also have several state collaborators and several academic collaborators as well. Our implementation plan is to dredge, as Laura mentioned, for 200 hours in the fall, in the spring, and in the summer. So the fall test occurred in September of 2025. And as part of that, we really used it as a big science experiment to determine what the optimal dredge parameters should be. And so we tested certain parameters such as the dredge location, the speed, the direction, nozzle spacing, and we assessed the effects of all of these different parameters on the reservoir bed and also the water quality downstream. And then from the lessons learned from the fall test, we are going to implement those lessons learned to the spring and the summer tests to optimize sediment removal while remaining within our permit restraints downstream. The dredge operations will occur primarily closer to the dam. So within the first 4 miles from the dam will be the majority of the dredging. And then some of the further tests away may help answer some of the questions such as density current transport, what that transport distance should be. And so we anticipate a little bit of dredging in the upper reservoir, but primarily focused in the lower 4 miles of the reservoir. The flows leaving the reservoir will be robust flows in order to ensure that the sediment transport, ensure that the flows are able to transport the sediment that's leaving the dam. And those flows will be adaptively managed to ensure that we limit the concentration in the downstream channel to the natural variability of what's coming into the reservoir. So our main goal is really that we manage the flows such that what's leaving the reservoir is similar to what's coming in as far as concentrations go. Here's our downstream monitoring plan. We have 5 continuous gauge stations on the Big Blue and Kansas River, and so those are measuring real-time turbidity and water quality measurements. And then we are also monitoring at several locations for pre- and post-project water and sediment quality measurements. So some of these include bed elevations, bed gradations, invertebrates, and water quality parameters. As far as some of the preliminary conclusions that we've gleaned from the fall test, we did not exceed any of the state water quality criteria or the conditions of our 401 certification. Monitoring results for the fall test, they remain below the treatment triggers for Kansas River water plants, so no additional treatments were necessary. We are collaborating and planning for ongoing adaptive management technical teams to mitigate any potential impacts to aquatic life, so we are continuing to adaptively manage during the following demonstrations. And then finally, the aquatic richness was lowest at the upstream control site 3 days and 4 weeks after the WID test. Downstream sites showed no apparent reduction in richness compared to the pre-test levels or to the control site.
Yeah, so I'm just going to provide a brief summary on, the data assessment for all the information that we're collecting during these 3 dredging demonstration periods, and then how we're going to share that information with internally and then externally as well, and then our post-WID reporting. So one of the outcomes are the products from the demonstration will be a project technical report that'll focus on addressing each of those primary questions that Michael mentioned earlier and describing the technical aspects, operations, the sediment production, water quality, and then downstream impacts. There'll be a number of appendices that will be included with the project technical report, main report, including information from the Corps of Engineers for data collection and analysis, and then data and technical reports from other researchers like USGS and K-State and just other entities that are supporting us as well. There'll be a USACE technical, a USACE water quality report, downstream sediment data / report, and then the USGS report and K-State, and that's mostly the downstream monitoring for the ecological pieces downstream. And then there'll be a number of journal technical articles by the Corps of Engineers and by other entities as well. Several journal articles will be co-authored by the U.S. Army Corps of Engineers documenting the sediment consolidation, density current transport, operational efficiencies of WID, and then potentially some other topics as well. KU, K-State, the Engineering Research Development Center, and Virginia Tech, we anticipate that there'll be some journal technical articles by those entities as well. There's some other things that this work can support, and this is not meant to be an all-inclusive list, but the data generated can be used to develop a Tuttle Creek Lake hydrodynamic model. This can be used to plan optimal dredging patterns in the future, if that is determined to be feasible, and then including the effects of dredging areas further upstream in the lake as well. The technology could also be applicable to other reservoirs such as Canopolis Lake and Perry Lake in Kansas, as well as other lakes with bottom discharging service gates around the country. The technology could also potentially be combined with a hydrosuction technology at other reservoirs for long-term management, such as John Redmond Lake and other lakes without bottom discharging gates. So we're looking at the potential for water injection dredging in those scenarios as well. But whether or not the water injection dredging is shown to be more cost-effective than traditional dredging, this demonstration serves as a test of the impacts of large sediment releases on the water quality And ecology of the downstream channel, which impacts can inform partners and provide data for the National Environmental Policy Act or on the effects of sediment management by other means. So there's lots of different ways that this data is going to be important and could be useful in the future. We do have a number of collaborators that are listed here, those within the U.S. Army Corps of Engineers. The Omaha District is supporting the Kansas City District as well as the Engineering and Research Development Center, the DOER program, and their environmental management program as well. And then the Sustainable Rivers program has been a part of just supporting this effort as well. And then other agencies like USGS, Bureau of Reclamation, and the National Science Foundation, and then a number of academic entities as well. And then, of course, our partner, the Kansas Water Office, and then other state agencies in the state of Kansas, such as the Kansas Department of Wildlife and Parks and Kansas Department of Health and Environment. So that concludes our webinar for the Tuttle Creek Reservoir Water Injection Dredging Spring period. And we want to thank you all for listening.